Hello, today we are going to look at applications of integration, or more accurately, one type of application of integration. There are several. And what we're going to focus on is the idea that integration is connected to rates of change. So we talked about rates of change in differentiation, where we were looking at the way that things changed in time. And we looked at the relationship between distance, speed, and acceleration, or in Leaving Cert language, displacement, velocity, and acceleration, and how they related to each other in terms of their derivatives. So if we had a displacement s, the velocity or the speed would be ds dt, the displacement relative to time, and the acceleration would be how the velocity is changing in time, or the second derivative of the displacement. So we already know those relationships, and we know that integration is something that effectively undoes or is the opposite of differentiation. So we're going to use that fact now and add to this understanding to allow us, before we were able to go from displacement to velocity to acceleration, now we're going to get the ability to go from acceleration to velocity to displacement. So move in the other direction, undo that differentiation. So if we think about displacement, if the velocity is the derivative of the displacement with respect to time, then if we integrate the velocity with respect to time, we would end up with the displacement. And of course, as always, we must add on our constant. So if we have our displacement, if we want our displacement and we know our velocity with respect to time, we could get the integral with respect to time and then add on a constant, which we would need more information to find, and that would allow us to get back to our original displacement. Likewise, if we had our velocity, do this as a separate one because we already have an equality going on there. If we had our acceleration and we wanted to get back to our velocity, we could get the acceleration and get the derivative with respect to time, and that would bring us back to the velocity. And of course, we must add on our constant that we might have lost when we had v and we differentiated to get to a. If we had a constant involved in v, it would have been lost. So we must add that potential constant back on when we're integrating a, because we wouldn't know what to put in as a potential constant otherwise. So these are our two new relationships, and they come directly from the fact that we know that integration and differentiation are kind of antonyms of each other. They undo each other. Very closely related, I suppose, to what we would have talked about with inverse functions. Now, let's take an example of a rates of change type question that now involves some integration as well as differentiation. The velocity in meters per second of a car is given by v is equal to this, and its initial distance from a fixed point is 2 meters. You could be told its initial distance from home or its initial distance from a crossroads, some fixed point that they're expecting you to measure from, to give you a concept of where you are measuring distances from. The other thing I have deliberately done here is putting distance instead of displacement, because in maths, unlike in physics and applied maths or in junior cycle science, we aren't as careful as we should be with language. So the exams will sometimes say distance when they really mean displacement. So we do need to be aware that in maths, distance and displacement are considered largely interchangeable, just like speed and velocity will be considered largely interchangeable. So we need to be conscious of that as we are working through. And I think I have just spotted So I just had a spelling mistake for my velocity there. Now, let's get into our question. We want to know the displacement after 1 second. So I have a velocity. I need to get displacement. I need to know by heart and understand that the velocity is the rate of change of my displacement. So I know ds dt. I want to get back to s. What other information is given to me in the question, though, is important. I'm told its initial distance from a fixed point is 2 meters. So initial is a key phrase in our work. Initial means t is equal to 0. So this is a key bit of language that will come up in the questions. What we're told is that when t is 0, you can write this in wherever we want, when t is equal to 0, s is equal to 2 meters. So that's the information that's given to us here. So we have the velocity, and we also know these initial conditions of at t is 0, s is 2 meters. So we have that. So let's start into part 1. I have v is equal to 9t squared minus 12t, and I know that t equals 0, s is equal to 2. And I know that that is equal to ds dt. So if I want to find s, that's going to be the integral of v dt plus some constant. So that's what I'm going to use now. The displacement is going to be the integral of my velocity with respect to time plus some constant that I'm going to use my extra information to find in this case. So if they didn't give you the extra information, you could just put down the constant c as we have before. So we get our integral, and we have s is equal to, increase the power by 1 and divide by the new power. Increase the power by 1 and divide by the new power, plus our constant. S is equal to S is equal to 3t cubed minus 6t squared plus c. Now remains to us to find c. Well, I know that when t is equal to 0, s is equal to 2. So 2 is equal to 3 on 0 cubed minus 6 on 0 squared plus c. Therefore, c is equal to 2. So s is equal to 3t cubed minus 6t squared plus 2. And then I want to know what that is equal to after 1 second. So I want to know what s is after 1 second. So s of 1 for 1 second. The variable in my displacement formula is t, so s of 1 would be a function's way of writing this. It would be 3 on 1 cubed minus 6 on 1 squared plus 2, which when you add it all up will be minus 1 meters. And this is an important point. Displacement, because it has a direction, can be negative. So we usually say that distances can't be negative. Displacements can absolutely be negative. We would usually take going to the right, as we would on our coordinate plane, we'd usually take going to the right as being positive and going to the left as being negative. So we might say that this means that we are 1 meter to the left of our fixed point after 1 second. So that's our part 1. Part 2, the acceleration of our car after 1 second, or at t is equal to 1, so that would be after 1 second. These are two different ways of writing the same time constraint. So we want to know the acceleration then. So if we know v is equal to 9t squared minus 12t, a is going to be equal to dv dt is going to be equal to 18t minus 12, and we want to know what that is at t is equal to 1. So we sub in t is equal to 1, and we have a at t is equal to 1. Again, our variable is t, so a at 1 would be a function's way of writing this. You don't have to write it that way. It's just to highlight to you that it is a method of writing it. and you could see it on the exams, and you end up with 6. And then our units for acceleration would be meters per second per second. So technically you can write it like this, it's meters per second, but more commonly you will see it written as meters per second squared, or potentially meters seconds to the -2, because we know that if we move this squared up on the top of the line, we would end up with a negative power on it. So exactly the same way as we can move around our numbers, we can move around our letters in our units. We get 6 meters seconds to the -2. Those are 3 different ways you might see acceleration written. And that is what we need for our application of integration, where we are looking at how the rates of change that we've already worked on in differentiation can be dealt with in integration. So we now have this ability, instead of going from displacement to velocity to acceleration, we now have the ability to go from acceleration to velocity, or velocity to displacement. And again, we need our conditions, we need our extra information to find those constants that we might have lost by our original differentiation. And that is what we need for now.